Hello and welcome to the session where we're going to review the risk estimation model. To run this, I've already preloaded a program, so there is some data in the workspace, and this doesn't really rely on anything from there. All we need is any data table like we've been generating. So I'm just going to choose this one. We can see in this simple data set, we have the usual student number, course code, year, semester, credits, test 1, test 2, and a final mark. And looks like in this, we also worked out the number of standard deviations. So we want to estimate the risk by evaluating the departure from the mean by each entry, right, by each student. So in other words, we want to look at, let's look at just these three, test 1, test 2, and the final. And these are marks achieved by each of these students. So we want to know, is this mark significantly different from the other students? And by how many standard deviations is that? So the number of standard deviations is a nice normalized way to answer that question, because then it's relative to the mean rather than being some absolute number. So we could have any column of values, and we would always be comparing the number of standard deviations away from the mean. So to do this, we head on over to data analytics, and you see as you select a table here, it will pre-populate that. And we've got the field set, which is basically the list of all the columns here. And we have a field. So that's all we need to generate the risk model. So we just need a label field. So we'll see just now that we get the selectors based on the title. So we can just choose student number as the title. And then as we mentioned, we are interested in these three columns. So let's cut out all the other ones. So we just want test 1, test 2, and final. So those are the fields that we want. And let's go ahead and save this in a new attribute in the workspace. So risk model. And we can just click on risk model. Again, that's under data analytics. So risk model. And this takes a few seconds to run because there are 1,000 points in this data set. So here's the result. And we can see, number one, that the three attributes that we chose are listed here. So on test 1, we can see the mean and the standard deviation, right? Too many significant figures here that needs to be fixed, but we can see the mean and standard deviation, the median, the number average. So if you know about the moments of a distribution, we can get the number average value. And then 100 students in this data set. And we can actually see all the values in the data set as well if we want. So that's there. The minimum, maximum, also the skewness and kurtosis. So the skewness is how far our points actually lean away from the bell curve, right? So in the graph here, we are looking at the spread, the distribution of all the points. So we can see the frequency of the values in particular ranges. So we are taking a delta X of 10. So if we look at 70, for example, this point here for, it's approximately 70. It's between 65 and 75 if delta X is 10. So I don't think that was used here, but if delta X is that value, then in that range, right, between 65 and 75, we can count up the number of students in that range for test 1, and then divide that by the total. That would give us the fraction. But this is, of course, also the distribution function. So it's the fraction divided by the delta X. So anyway, this is the distribution function. So the orange dots are the mean and standard deviation. If we apply simply the mean and standard deviation in the normal distribution formula, then we can generate this orange set of dots. So that's your normal distribution. the mean and standard deviation were calculated from the actual data, which are the blue dots. So ideally, these blue dots would sit close to the normal distribution, but you see there's a fair departure away from that. So this data doesn't perfectly fit the normal distribution. Still, it can be useful to work under the assumption that it's a normal distribution. And in fact, many of these points are actually close together. So there's a higher density of these points than we might imagine there. So that's test one. So those are the stats for test one. And then if we look at test two, we can also see the distribution around that there, as well as for the final. So we can get the statistics for those three, you can say, measurements of the students. And then because we chose the student number as the title field, you can see that's the label there. And if we click on view results, you can see the results for that student, the three attributes that we chose, along with the standard deviations. So for instance, here we have a relatively high value. So we know this 87 is a high value, right? If the average in the class was 87, then this would not be a relatively high value. But we can see here, because the Z value is 1.58, we are more than 1.5 standard deviations above the mean. If we look at test one, you can see the mean there was actually 72, and the standard deviation is 9. So we are significantly higher than the mean in test one. So that's why we classify this student as being high performing. Right, so high performing here. So you can look at any of these results and you can see all these students have relatively high values for their assessments. And then we also have low performing. So you can see these students have relatively low standard deviation. So minus 1.6 means more than 1.5 standard deviations below the mean. So that's how we can estimate whether it's high and low performing. The actual way that it determines whether it's high or low performing is by determining these Z values and by raising alerts. So here, number one, it's saying those marks are below 50. So there is also the possibility of setting that there's an absolute value to look for. So Z values are not absolute. Those are for relative numbers, but we can, in our settings, prescribe a minimum value below which we raise an alert. So here we have raised alerts simply on being below 50. And then also, if it's a relatively low mark, again, going to the risk settings, relatively low means we are less than one standard deviation, more than one standard deviation below the mean. So we can change when an alert is raised on the number of standard deviations, and we can change the alert when we go below a certain value. Of course, if you want to switch this off, a kind of workaround to switch this off would be to set the minimum in all the data. So if you set this to a 0, for instance, then a student will never have a mark below 0. So that's a way to switch this off. Similarly here, for your standard deviations, I guess if you use a value around -5 or something like that, there's no student with more than 5 standard deviations below the mean. I think it's something to check in the source data, of course, and you can always do that here. So that's how this method works. It's quite general. Of course, we've been talking about this in the context of students and risk estimation, but you can use this for any set of data. You can just choose the values over which you want to test for the standard deviations. You can choose a label field and then just click risk model and it will generate this interface. So that helps us identify high performing, low performing. You can also view all the entries together. And by the way, there's a little filter here. So as you start typing in here, that will filter the list, and you can page through all the entries as well. So that's how we can classify high performing, low performing, and so on. And there is a little download method here as well. So you can download all that data. So that's the risk estimation method. Thanks for listening.